Hello everyone. This is going to be sort of an intro video for assignment 3 this semester. And as soon as this new simulation finishes opening that I just started, we will go through and start to look at this. But just the high level recap. The details of the assignment are in Canvas. However, basically this is a supersonic wedge simulation. And we're looking at supersonic flow for starters over a wedge that is going to generate a shock wave. And we need to look at different physics to some extent and different values. And we need to have an idea of where that shock wave is before we even really mesh this thing entirely. So let's go ahead . Yeah. Let's go ahead and create the wedge in question here. So there are a couple different ways to do this. I specifically am going to use a 3D CAD model for this. You could also use a block and a cone and another block and cut it out that way. I'm going to use the 3D CAD because this ought to be a little bit easier in this case. So let's go ahead and create a sketch on the XY plane. This is two-dimensional, like all the other simulations. So what we're going to do here is the wedge is going to start at the origin. It's going to be our first really definition here. And other than that, we have the angled wedge, a flat region downstream of it. We have a vertical for the outlet, a vertical or another horizontal for the top surface. We have a horizontal run-up, and we have an inlet. So this is schematically what our domain looks like, but the dimensions are all wrong. So let's go and add some dimensions here. So I'm going to left click on all these, and I'm going to name all of these. So these are going to be changeable. Here we're going to add a angle dimension. There we go. So I would have preferred the angle be labeled in here, but this is our deflection angle. Let's see here. What I would like to do. Why isn't this anchoring? That is definitely a construction line. Okay, we're going to do this the hard way then. There we go. This is a vertical line. This is also a construction line. And really the only reason I'm doing this is so that we can apply a length dimension here. Oh, no, that is not construction, but this also has a length dimension. So we have a run-up length, a ramp length, and a relief length. Let's see here. What I'd love to do is, and this thing is something I'm not quite 100% sure how to do right off, is to set a driven dimension. This isn't quite the domain height, but it's close enough. And then this should be driven. So I want this leading edge of our wedge be at 0, 0. And then I can fix that. I think this should be constrained pretty fully at this point. This is our domain. Although, incidentally, I want this height to be 5 times this. But I'm not 100% sure what a good way to do that is. So I did say at minimum, so we're going to make this something like 0.75. And that is going to make the total domain height a little bit more. It's actually about 6 times that ramp height. And we're going to make this deflection angle 8 degrees. If I make that 0.6 instead. Okay, so this is our domain. We can take this sketch and extrude it. Doesn't really matter how far we extrude it. And this is going to give us the solid body that is going to be our part. So there's our CAD. We can take this and we can say, create a new geometry part from this. The defaults should be okay. But also, I'm going to go through and edit this to make things just a little bit neater here. And name some of these faces. Take this, and we can rename this and say domain. There we go. So now we have, theoretically, everything we need in there. Let's create a scene, a geometry scene, just to make sure. We have default is actually empty. We have an inlet, we have an outlet, we have an out of plane, we have a ramp, we have a relief, we have our run up region, we have our top surface. Okay. Now I'm going to actually do something here, and this is going to be to create actually I should probably rename this body. Main. We're going to do another sketch on the XY plane, and this is going to be something we're going to potentially use later. But it's just going to be a pair of circles here. The radius is going to be something I'm going to change a little bit later. Let's see here, actually. Rename, show only, create sketch. Project to sketch as construction. Okay, there we go. That's what I needed. So what we're going to do here is apply a radius dimension. We're going to call this relief control radius, and we're going to call this centimeters. We're going to call this 1.5 centimeters and call this the ramp control radius. Okay. We're going to extrude this. Now we are not going to merge. These are going to, we want new bodies. And we're actually going to do a two-way symmetric just to make sure these cylinders do what we need. And actually, I think I named those backwards if I'm looking at this correctly. Oh, no, I didn't. I know what happened. Okay. Make that just a little bit bigger just to be safe. Okay. 3D CAD, close. And we'll say update. Actually, I should name these. Rename. So actually, if I delete that, I can say new geometry part. Create part from CAD solids. I believe we do not need these to be coincident. We're not interacting, just some of these. There we go. Okay, perfect. Let's try that again. Let's go ahead and create a new scene again. I'm going to delete the old one for cleanup purposes. There we go. Okay. So we're going to need we don't need a wedge there. Okay, perfect. I think that should be what we need. So we will need a little bit of extra for in terms of controls to mesh this thing once we get to that point. But this is honestly most of what we need. So this is going to be supersonic, so this is going to throw a shockwave. So we need something to refine where that shockwave is. I'm going to do that with a part. I'm going to make a block. Actually, I'm going to make a cone, excuse me. that does this. And what we're going to do here is we're going to say the start is going to be ever so slightly actually, should I parameterize this? That's probably good enough. So this cone is what we're going to use to refine the shock wave. Call it a shock refine, or actually shock control. And notice I just left it horizontal. That's because I'm going to rotate it. So I'm going to rotate the shock control about the origin, about Z, and it's going to be by whatever the beta angle should be. So let's see here. I come over here. Bear with me a second. Haven't actually decided on a Mach number yet, but we can take this angle. Let's just say Mach 1.8 is probably about right. So let me open this and we'll put this image up. Yeah. So if we look at Mach 1.8, our deflection angle was 9 degrees, I believe. So we're expecting our beta angle to be somewhere in the neighborhood of, it looks like about 43 degrees, give or take. We're going to rotate this by 43 degrees and start there. And actually, we can sort of name this if we make a parameter. We can just call this beta angle, and then we should be able to rotate by our beta angle. This is a little bit fancier. You don't have to do this. You can just hard code a number. Don't worry about it too much. But we can absolutely rotate this, and in theory, that actually rotate. Not yet. Forms rotate that about Z. Let me see here. It's possible. Okay, that's curious. Why isn't this rotating? bear with me a minute here. This is curious. Okay, well, we'll proceed for now and see, because I think this might just be a graphical thing, but I'm not 100% sure. So, we badge our domain for 2D meshing. We have all of our surfaces, which is great. Now, let's try and make a automated mesh 2D for our domain. We'll use a polygonal mesher and a prism layer mesher, and we are going to go ahead and make our domain a region. Assign parts to region, a boundary for each surface, and a region for each part. So the controls that I always make sort of by default are a far field refine, so we don't accidentally make 2, 3 run up. We don't accidentally make all of our boundaries super small. And this is just going to be a modified target size. I'm going to say 800%. We need to change our base size probably to, I'm going to say 0.5 centimeter. And let's just mesh this and see what it looks like. Scenes new, mesh scene. Okay. We definitely are going to need to also get rid of our prism layers on these other surfaces. We're going to need to modify a whole bunch of things. So we want to make a maximum size. Let me rename this. This is going to apply on our plane, and what we're going to say is the target size is now 800%. What this does is says that the largest any cell can be anywhere on this surface is 800% of the base size. And we're also going to turn the growth rate way the hell down. Actually, I'm going to turn it down even further than that. I'm going to turn it down to 3%. This is going to grow real slow now. Boundary layer. We want to change some of the boundary layer defaults. Let's go with about 12 prism layers. And then the thickness, let's say 50%, and see what that looks like. That's not bad, at least so far. So we're going to need a couple more controls for sure. One of these is going to be, well, these are all going to be volume controls, incidentally. One is going to be that ramp control. So this is going to be shock LE refine, which is the leading edge of the shock. Because we expect the shock rate to start there. Actually, I'm just going to delete that, and we're just going to use the cone. I really wish I knew why this cone wasn't Wasn't rotating. At least it sure doesn't look like it's rotating. Oh, it's rotating about X. Duh. That's why it's not rotating. There we go. Okay. I am not immune to dumb mistakes like that. Let's see here. There we go. So now we can actually rotate this up around our beta angle. Hey, perfect. There's our shockwave. That's what we wanted. I was just rotating about the wrong angle. That's fine. We figured it out. So we want to change the mesh in this area. And we're going to say the mesh in this area is going to be... Oh, I might regret... Okay. Let's say 50%. And mesh this and see what it looks like. Okay, there we go. So we're up to 43,000 cells. 50%. I'm definitely glad I didn't do 10%, mind you. But let's be a little bit aggressive and go down to 10% or 20%. These are going to be 1 millimeter cells. These are going to be bigger than the shockwave, for darn sure. But they're going to be smaller than anywhere else. Let's see here. 0. I realize the cylinder isn't quite what we're going to want over here, so we need to refine this a little bit. And then angle. Call it 45 degrees, and we'll call this the expansion angle. Rename. This is going to be expansion control. There we go. Close, update. Oh, it's not called the right thing anymore, so let me just rename this manually, I guess. Rename. There we go. Okay, so we have our shockwave control. I'm doing some fancy things. You can just do a basic cone and hard code it. That doesn't matter. But we have a region where we expect the shockwave to be, an approximate angle where we expect it to be, and the cells are much smaller in that entire region. We're also going to create a new volume control for the expansion refinement. And again, this is a volume control. We are going to edit the size in this volume to say 50%, I think. It's going to be relatively small, but definitely not as small as the primary shockwave. This is probably going to land us at a couple 100,000 cells, give or take. There we go. That looks reasonable. And then our transition looks reasonable over there. It even looks mostly reasonable over here. So I think this is actually looking pretty good so far. I think the next thing is just to really set up the physics, and then we'll give it a go in physics and then boundary conditions. And then we will attempt to simulate this thing. So it's going to be steady. We're going to be looking at a gas. We'll try segregated flow. If it gives us problems, we might need to do coupled flow. This is going to be the Mach number regime where coupled flow very well might be necessary. So this is extremely borderline. But we will try segregated flow, ideal gas, K omega turbulence, segregated fluid temperature, and I don't think we need anything else here. That should be okay. It's going to assume air by default, which is fine. So for our boundaries, we are going to have a free stream inlet. The outlet and the top are going to be pressure outlets. And also, so is we're going to call this a symmetry plane, is our run-up region. Because if this is a wedge, it's not going to generate a boundary layer up here. So the symmetry plane is going to say there's not going to be a boundary layer here, but no flow can cross over that. The relief is a wall, the ramp is a wall, that's all fine. So we are going to specify our Mach number of 1.8. I think the default is fine for the rest of this. So let's go ahead and create a new scalar scene for Mach number. And the lab reference frame is fine. We don't have another reference frame, so that's the only choice we have. And save. And I'd like to see what is going on here, so we're actually going to go to our scalar 1 scene and have it display our mesh. We can see what is going on here with a little bit more accuracy. So it's going to take a while to figure out what's going on once it hits this smaller mesh area. So we're actually going to try something. So to date, what I've just kind of let the default assume is really that the initial condition is 0. The initial condition is no velocity. Let's try and give this an initial condition here. So I'm actually going to create a couple more parameters. We're going to call this freestream mock. We're going to call this 1.8. Parameters new, scalar. Freestream temperature. 300 Kelvin is fine. And we're going to create a derived value. Freestream velocity, which is going to be length per unit time. So 1, -1, distance over time. And this is going to be calculated. Let's see here. So this is going to be whatever the freestream Mach number is, times square root of gamma RT, right? So I'm going to hard code air. So gamma is 1.4, R is 287, and then temperature is that. And then it's the square root, so 0.5. Okay. Let's see here. This should evaluate out to something. And we should be able to set an initial condition of our freestream velocity. But it doesn't seem to like that. So I may have messed this up somewhere. It is calculating that properly. Times freestream Mach times. Dang it. 87 times. Oh, okay, I guess I just needed to tell it this was composite instead of... Sure, I guess that'll do. Okay, so now if we initialize this, it initializes to a velocity everywhere. So it's actually looking like this is going to be a lot faster, like already iteration like 100. We have a decent idea of where that shockwave is, which appears to be forming more or less where we expected it. And then we do indeed have some expansion effects occurring inside this fan region. So we're going to let this sit here for a little while. And just to make sure the flow field is more or less stable, we need to generate some reports. So let's go ahead and generate a force report. This is just going to be drag on this wedge. So on the ramp and the relief collectively, we're just going to measure drag. Create monitor and plot from report. We are also going to show, let's see here, let's see here, a surface average, metrics, surface average, yeah, there we go. So on the ramp, because we expect properties to be constant over the ramp, so the average is going to be reasonably accurate. We can just look for static pressure. And see what do all these values look like. And incidentally, we should also probably create some scenes. Honestly, this is already looking pretty converged. I'm not particularly liking this little effect up here. But I think that's an artifact of the interaction between the shockwave with this boundary. But importantly, that shockwave is where we expected it to be. So let's see here. I'm going to try something here. This should be relatively easy. And we're going to go through and edit the 3D CAD. And we're just going to make this domain a lot taller. So we're going to call this domain height 2 meters. Okay. Update 3D CAD, close, and now we're just going to have it remesh. It should automatically update everything. There we go. And it did try and figure out what's going on. We don't even need to restart the simulation, I don't think. Oh, it stopped because of a stopping criteria. There is the default 1,000 iteration stopping criteria. We'll let that keep on going. So honestly, it doesn't look like we needed this cone to be as big as it is. We can make this run a little bit faster, or honestly, probably a lot faster, by editing the properties of this cone. So instead of 1 centimeter leading edge, we're going to make this like 0.5. Instead of 6, we're going to make this like 2 for that. And we're going to mesh again. So this should make... Actually, let me stop that. We are, however, going to make it longer. So instead of 1, we're going to make this 2 meters. And now we're going to mesh again. So it's going to be... might have overcooked that a little bit. We'll see here. I'm going to turn it down by a degree, I think. Theta angle, 42 degrees. Let's see here. If we update this transform, click on this. There we go. I think that's probably better. But we are probably going to need to make this just a little bit bigger. 0.6. Let's try that. See what that does. I think that ought to be a lot better. Well, at the very minimum, it will change the number of cells quite drastically. And we should be able to tell it to run again, and it should run a lot faster. We have a shockwave, an expansion fan. Some slightly weird effects up here at the outlet, or at the top outlet, but the rest of this is extremely well defined. So we can look at some other scenes. You should look at other properties as well. I'm not going to look at everything here that I expect you to look at. But let's look at a couple of things here. First of all, scalar, let's look at total pressure. Okay, so we get some weird effects on the top there, but we do indeed see there is a total pressure drop across the shockwave. So we probably need to limit the range. If we just let this auto range, it's going to do dumb things, honestly. So let's say the minimum will be 300,000. Max will be 520,000. And clip is going to clip off anything 400,000. There we go. Okay. So there are some interactions from this corner up here that's doing some weird things. But we indeed do get a total pressure drop across the shockwave and a loss of total pressure inside the boundary layer, which is also what we expect. So we do indeed see exactly what we expect. We do not see a drop in total pressure across the expansion fan, which is also what we expect. So this is doing what we expect from the total pressure perspective inside and around that shockwave and that wedge. Let's also make a new scalar scene for temperature. Again, you can look at other values as well, density, etc., but we see that there is a elevated temperature inside the boundary layer for starters, and a noticeably elevated temperature behind that shockwave, which is a very straight, clean line, as well as a temperature drop through that expansion fan, which is exactly what we expect. And we can sanity check all of these ratios with a basic shock calculation based on the turning angle and free stream Mach number and things like that. But this is basically what assignment 3 is. You will need to do more configurations than just one. Very clearly, you'll need to use different values, and you'll need to compare it against supersonic flow theory to see if these values actually do make sense. But this behavior that we're observing conceptually absolutely does make sense for what a shockwave should be doing in this scenario. So I'm going to save this, and I'll go ahead and upload this, and you can take a look at this at your leisure. This is conceptually what assignment 3 is.